Inside the human chest, a silent sentinel keeps watch, a device no larger than a silver dollar tasked with an impossible mission. This is the pacemaker. It must function flawlessly for over a decade, submerged in the corrosive, salty environment of the human body, all while delivering precise electrical pulses that dictate the very rhythm of life. To achieve this, engineers must bridge the gap between delicate silicon electronics and the harsh biology of the person it protects. We are talking about a machine that cannot be repaired once it is installed, one where battery failure or leakage aren't just technical errors, they are life-threatening events. Today, we explore the extreme engineering to build these miniature marvels, specifically the secrets behind their long-life power sources and the impenetrable hermetic seals that keep the outside world out and the pulse of life going. From high-energy chemistry to laser welding at a microscopic scale, this is the journey of an electronic heart, starting from the raw elements to the final, life-saving click of the lead wire. The heart of the pacemaker isn't a heart at all, it's the battery. But this isn't the lithium-ion cell in your phone. Those are prone to outgassing and require recharging. A pacemaker needs something far more reliable. Enter the lithium iodine cell. This chemistry is unique because it is solid state. There are no liquids to leak. When the lithium anode meets the iodine cathode, a layer of lithium iodide forms between them. This layer acts as the electrolyte. And here is the engineering magic. As the battery is used, the layer naturally grows, increasing internal resistance and creating a predictable, gradual voltage drop. This allows doctors to predict exactly, down to the month, when the device will need replacement, years in advance. These cells are designed with ultra-low self-discharge rates, essentially sitting in a ready state for over 10 years without losing their punch. They are the marathon runners of the energy world, delivering microamps of current with surgical precision, year after year after year. To protect the delicate battery and circuitry, engineers turn to one of the most biocompatible materials on Earth, titanium. Specifically, grade 5 medical titanium. It is incredibly strong, lightweight, and most importantly, the human body does not recognize it as a foreign invader. The process begins with two precision-stamped titanium halves, known as the clamshell. These shells are polished to a mirror finish to ensure there are no microscopic pits or grooves where bacteria could hide. But the challenge isn't just the shell, it's the entry points. The pacemaker must connect to the heart via wires, or leads. This requires a header, a transparent block of medical-grade polyurethane or silicone resin. This header acts as the interface between the internal electronics and the external leads. It must be perfectly bonded to the titanium to prevent even a single molecule of water vapor from entering, because inside, the electronics are so sensitive that a single drop of moisture could cause a catastrophic short circuit. How do you fuse two pieces of metal together without damaging the heat-sensitive battery just millimeters away? The answer is precision laser welding. The titanium halves are placed in an inert atmosphere, usually pure argon, to prevent oxidation. A high-energy fiber laser then traces the seam, focused to a spot size smaller than a human hair. The laser pulses so quickly that it melts the titanium locally, fusing the halves into a single continuous piece of metal, a process called hermetic sealing. This isn't just a waterproof seal, it is an airtight, gas-tight barrier. To verify the seal, the device is placed in a vacuum chamber and sniffed for helium. Helium atoms are so small they can leak through holes invisible to any microscope. If even a few atoms of helium escape the device, it is rejected. This level of sealing ensures that the internal electronics stay in a bone-dry, ultra-stable environment for the entire life of the patient. The greatest engineering challenge is getting electricity out of the sealed titanium box without breaking the seal. This is the job of the feed-through. It is a masterpiece of material science. Tiny platinum or iridium pins must pass through the titanium wall to connect to the header. To keep these pins insulated and the box sealed, engineers use aluminous ceramics. The ceramic is brazed to the titanium using gold or niobium as a filler metal. Why gold? Because it resists corrosion and flows perfectly into the microscopic gaps. This ceramic-to-metal bond must withstand the constant pulsing and temperature shifts of the human body without cracking. It is a bridge between two worlds, allowing the brain of the pacemaker to talk to the heart, while maintaining a wall that is essentially as solid as a single piece of stone. The precision here is measured in microns, ensuring the path for the electrical pulse is clear, but the path for moisture is forever blocked. Before the shell is closed, the brain must be installed. This is a custom-designed application-specific integrated circuit, or ASIC. Unlike the processor in your laptop, this chip is designed for one thing: extreme efficiency. It consumes less power than a single LED on your standby TV. The circuit board is a multi-layer sandwich of polyamide, flexible enough to fit into the rounded contours of the titanium case. Every component is surface-mounted with high-precision robotics and then underfilled with epoxy to protect against vibration. These circuits don't just shock the heart, they listen. They monitor the heart's natural electrical signals every millisecond. If the heart skips a beat, the circuit detects the pause and triggers a precisely timed pulse. It's an incredibly complex dance of logic gates and capacitors, all working together to ensure that the patient's heart never misses a step, while surviving on a power budget that is virtually non-existent. Before a pacemaker can ever be implanted, it must prove it can survive. The testing phase is brutal. These devices undergo accelerated aging, where they are placed in saline baths, heated to mimic the body's internal environment, but at higher pressures. They are subjected to intense electromagnetic interference tests to ensure they won't fail near a microwave or a storefront security gate. Engineers use X-ray inspection to look through the titanium shell, checking every laser weld and every gold-brazed joint for voids or structural weaknesses. They are vibrated at frequencies that simulate a car crash or a fall, because once this device is inside a patient, there is no undo button. Every single unit produced is individually tested, not just one from every batch. In the world of medical engineering, the standard isn't good enough. The standard is absolute, unwavering perfection. 100% reliability is the only acceptable metric. We have arrived at the final form. The titanium is polished until it shines like a jewel. The header is clear, the serial numbers are laser etched into the metal, providing a permanent record of its origin. This small object represents decades of progress in chemistry, physics, and microelectronics. It is a testament to human ingenuity, taking the most basic elements like lithium, iodine, and titanium and transforming them into a device that can restart a human heart. It is more than just a machine. It is a promise of more time, more memories, and more life. As the device is sealed in its final sterile packaging, it carries with it the work of thousands of engineers who refuse to accept the word impossible. The hermetic seal is tight, the battery is full, and the silicon brain is watching. The Guardian is ready to begin its 10-year vigil, ensuring that the most important rhythm in the world, the human heartbeat, never stops. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.